we're here at the 2019 Wolfram Technology Conference. I'm Sylvia Haas, and I run the social media for Wolfram Research. And I'm here with my co-host.
I'm Shruti Ponce, and I was a student at the Wolfram High School Summer Camp this year. And we have with us Jon McLoone, who is the Director of Technical and Communication Strategy, and he is going to be giving us a talk on diagnosing colon cancer with image processing.
So what do you do at Wolfram, and what has brought you to the talk?
Well, I have quite a lot of varied roles at Wolfram. I've been here a long time and I've got fingers in lots of pies. But in the context of this talk, one of the things that I do is I lead the technical services team in the European office. So we take the Wolfram technology and then we tailor it and build applications on top of it that make it suited to the actual task that the customer wants, rather than just giving them the building blocks to do it themselves. And so I'm talking about one of the projects that we've done within that team.
Okay, awesome. So what is this talk about?
Well, we're in a consortium with the NHS, the UK National Health Service, and some of its funding bodies, the University of Barcelona, and a couple of other partners to try and improve the way that bowel cancer is detected. At the moment, the ultimate way that it's diagnosed is with endoscopy, which is basically inserting a camera and fiddling around, and it's pretty unsatisfactory because it takes a lot of skill. You've got to be able to pilot this thing and diagnose at the same time, so that's a double skill set. It needs a hospital to do this, and it actually carries risks. There's a risk of perforating the bowel because you're clumsy with it. So the new idea is to take these miniature cameras that can be disposably created into a pill-sized capsule. You swallow it and you get a video all the way through, so you don't have the risk of missing a bit because you get a photograph of everything, and then reviewing that. You don't need any hospital, you can take this thing at home, there's no risk, and so there's a lot of pluses to it. The downside, though, is that it generates a lot of images. So you've still got a really big diagnostic problem that you've got this thousands and thousands of pictures, and how do you review those? And that's where it's thought that some image processing and automation could make this not just feasible, but actually, if it was simple and cheap enough, one could intervene early and be much more ready to do this kind of diagnostics. And actually, bowel cancer is very treatable if caught early. So there's a real potential upside to this one.
That's awesome. Do you have any examples?
Yeah, so I've got here some of my slides here, setting up the scene. This is the kind of what we're competing with. But this is actually the kind of thing that you end up with, and it's totally self-contained, and it's got enough battery to last the journey, and you just, as I say, you swallow it. But the challenge here then is how do we process all of this data? So one of the things that we're trying to do is to ultimately do this by machine learning. And in theory, with enough data, you just have to tell it, these are cancer spots and these are not. But the challenge at the moment is we've got no real data. So there's a couple of steps to that. First of all, we have to build a tool that allows you to collect the data. And then we want to be able to turn that into something that will auto-diagnose, or at least assist diagnosis. So this is here the kind of early prototype of the tool that we're putting together, and the idea is you select the video file that's been uploaded from the camera, and then we get this validation interface here. And this is now going through that video frame by frame. We can mouse over it, we can have a look at these close-up images, and somebody who's got expertise can look at that and say, yeah, that's clean, you're fine. And there's an interface then for marking all or some of those images as clean and unclean, and this is building that training set. Because ultimately you want to go back and then give the machine learning those tools and have it learn what looks like cancer and what doesn't. But in the intermediate step, one of the things we want to do is to mix human knowledge and machine knowledge, because with millions of images, the machine's going to do a better job in theory. But we're not going to have those at the moment because we're in pilot phase. So what we're trying to do is to accelerate the machine learning by also overloading some information that we have that we can choose from a human point of view. And so that's the classic image processing. We know things like there are bubbles in the images. So here's the kind of one of the problem things that comes up in images, with enough data to learn that's a bubble and to ignore it. But because as humans we know that bubbles generally have these kind of high entropy edges because they reflect off the light on the camera, then we can target those in a programmed way. And we have some filters here to try and improve the images by removing obstructions. So here we've this debubble function that we've written can automatically take out the area where you can't see anything because it's obscured by bubbles, and now the machine learning can only see the actual bits of the bowel. And there's a couple of other filters that we have that are taking out things like obstructions. So this is some of the inputs and the outputs, where the white area represents the mask of the bit that we don't want the machine learning to see. And that way we can have it only focus on the bits that matter. So in theory, fewer images will still produce a useful signal from machine learning.
So what's like the target number of images for a training set like this?
Well, to some extent that's up to the other partners to try and generate. So, we'd like it to be in the thousands. It would be better if it was in the tens of thousands. But it's a bit asymmetrical because even when you've got somebody with stomach cancer, you've got 1,000, 10,000 images of good intestines that you're not riddled with cancer unless you're in the final stages. So you're always going to have a fairly small number of actual examples of cancer. So we need a lot of those is the most important thing that it can learn from, which unfortunately we don't want to see. But in order to succeed, we have to see those things and tag them.
Interesting.
What inspired you to do this project?
Well, we've been working on previous NHS projects, and we've ended up making some friends in the NHS. We did a project before, taking some data from it was operational data from an NHS ward, and that was a very open-ended project where they just said, we've been collecting this for years for operational reasons. There must be something useful in this data. Tell us something useful. And it's fun to do projects like that where we just went through looking for patterns and correlations. And in that project, we found two really strong signals that are kind of an amusing example, actually, of exploratory data, because we found that we were looking at slips, trips, and falls. And it turned out two things that were strong indicators. The ratio of trained nurses to untrained nurses, so junior nurses, not the number, but the proportion. If there's a lot of junior nurses, people fall over. They're not being supervised properly. And the other one was that if people were sick, they don't fall over, which is kind of, when you think about it, it's because they stayed in bed.
Yeah.
So they don't have a chance to fall over, and the logical thing is to stop them falling over, make them sick, which is not really what the health service wants to hear. But that first finding made a bit of a name for us in the NHS, and so when projects like this came along, then people come to us knowing that we can handle the data and do the machine learning and the image processing and all of those kinds of things. So it came to us, basically.
Okay, that's awesome.
But it's good to do something useful.
Definitely.
So how long do you expect it to take for a fully trained data set, or a fully trained machine to come
Yeah,
up?
so the project is intended to last between 1 and 2 years. We got off pretty fast by getting our bit out in the first few weeks because, Wolfram Language, it meant we could actually do our bit quite quickly. We're now kind of in the waiting phase where the actual practicalities of getting it deployed in front of people and scaling it up, start generating the data, that we're going to have to wait some months for. So as soon as we actually start getting some data in, then we can start making the steps towards a tool that will be the next stage of this. Will be similar, but instead of just saying here's image 1, here's image 2, the idea is it'll start using the early results from the machine learning to say here's the worst looking image. This is the image out of all 10,000 that we think looks most cancerous, and then the doctor can review that first rather than having to go through thousands of images and say yes or no, and then start jumping forward saying no, and when you get to the super safe ones, perhaps he starts not having to look at those. So it's all going to be an iteration, and the question is, at what point does it stop being a chore for the doctor and start being, useful? Once that here's the worst image starts actually hitting the right image, then it's doing some good rather than in the training phase. But the idea is to make this virtuous loop that the more you use it, the better it gets.
Awesome.
After this project is complete, where will we be able to get more information or find it?
Well, it's publicly funded, so this will all be published at the end. So hopefully we will have some good news and we can make some headlines, but it'll at least be somewhere in the journals. There is a plan which hasn't been funded yet, but we're proposing, which is all about the rollout. So we're anticipating success, and our part in that actually is still going to be data science. But obviously there'll be maintenance on the tool, but one of the next steps is again practical, which is who's going to use this and who on. And there's some reason to believe that there's enough data already to be able to look at the patients and say, well, for you this would be the right thing, but perhaps for you it isn't. Maybe for certain ages it's more compelling that in a certain hospital where they've got very efficient and very cheap traditional methods, maybe it's not cost effective. And we're going to be doing some machine learning and data science to try and convince the people who should be using it that they should be using it, and B, to allow them to use it most efficiently on the right people to get the most cost-effective and best outcomes.
Interesting. So, is there anything else you want to tell us?
Well, my hope is that this is going to be one of those things that makes the world a better place, and I think the broader thing here is that, particularly in health is perhaps one of the biggest areas where there's a lot of unused data. There's already a lot of images out there that have been captured, but they're not labeled. And in other places, there's data that's perfectly labeled but isn't well structured. But the biggest thing I see actually on health data is access. That concerns about privacy override the utility that's buried in this data. And I have this kind of great fear, I tell this apocryphal story sometimes of imagining my daughter when she's in her 60s or 70s, and by that point, whatever's wrong with her, they'll be able to say, this has been seen 1,000 times before, 10,000 times before, and out of those we know, people exactly like you with exactly that condition, and all of the treatments have been tried, and we know which one is best, but I can't tell you because it's private data.
Yeah.
And if we can overcome that barrier and make it so that projects like this can access the anonymized and suitably protected data, there's just so much that can be improved in health. And this is just one tiny, tiny corner of it. You just multiply this over every procedure that's out there that's capturing data, and a lot of medicine is trial and error, and we're not learning the lessons of that.
Yeah,
If you look at things like a new drug, a huge amount of money is spent on a trial for a relatively small number of people. Drugs tried on 1,000 people in very controlled situations, and they control away the variability. They pick people who only have that one disease, who are the right age group, because they want to get the most out of that experiment. The real experiment's when the drug's actually out there in the market, and it's being used on tens of thousands of people with lots of other problems, and across a range of ages and backgrounds and weights and all of these variability, and yet we're not treating that like a valuable experiment, even though we're doing that experiment on live, real people every day.
A little terrifying.
Yes. But an opportunity.
Yes, definitely. Well, thank you so much for coming in and talking with us. When I read colonoscopy talk, I was definitely nervous about it, but this has been super educational and I think really awesome.
And it's a simple idea. It seems kind of obvious that we should be doing this, but we need to make it practical as well as simple.
Yeah. Well, thanks for coming
Thank
out.
you for coming.
Thank you.